Before we get into talking about logarithm in terms of calculus, let's take a trip back and review a little bit about logarithm as it evolved in algebra. Now, some of this discussion will be just historical in nature, and some of it will be quite useful. I'll tell you where the difference lies. But you started your discussion of calculus, your discussion of logarithm back when you had exponential functions. You talked about exponential functions, and you dealt with probably a very degenerate exponential function, kind of like f of x is 2 to the x power. Exponential functions, incidentally, are those functions that have variables in their exponents. Okay, so you investigated the graphs of exponential functions. You talked about domain and range. You talked about the nature of the change in the graph through the changes in values within exponential functions, and you looked at transformations of those functions. Then you turned attention to exponential equations, and you solved a number of exponential equations, and then you bumped into a very important problem. We painted ourselves into a mathematical corner when we got to even as a simple exponential equation like this, 2 to the x power equals 5. And we couldn't solve this. There was just no way for us to deal with an accurate solution to this kind of equation. We're trying to get into the exponential world in order to solve this. And the ticket window is sort of closed. But we open that ticket window by introducing the notion of logarithm, because truly the notion of logarithm is the notion of exponent. The logarithmic world is the world of exponents. And the first thing you did when you talked about logarithms was that you talked about this exponential form corresponding to this logarithmic form. Now notice the log form and the exponential form. And I know this is reviewed to you, but it's kind of important for you to know where things lie, where the numbers here lie in terms of this logarithmic form. This base of the logarithm is this base in the exponential form, the base of the exponent is this logarithmic base. The x, which is the exponent over here, appears in this position. So the logarithm of a number in a certain base is an exponent. So that's why the world of logarithms is the world of exponents. All right, and the number 5 appears in this position. Okay, you learned about how to go from exponential form to logarithmic form, and also how to go from logarithmic form back to exponential form, and you practiced that a good deal. Later on, you found out that in solving problems in the logarithmic world, you often had to go into the exponential world, into the exponential form, and to solve problems in the exponential form, you went into the logarithmic form. So those two forms played a kind of a reciprocal role. And as a matter of fact, they play actually an inverse role. And you saw that when you graphed logarithmic functions. You found that logarithmic functions, the family of logarithmic functions, were inverses of the family of exponential functions. Okay, so you did all of that kind of thing. We talked about, we took this form and we talked about various logarithmic bases, and we said that, gee, the logarithmic base 10 occurs so often that we don't even write it. When we write the log of x, we are really writing log base 10 of x. So we say, okay, this is kind of a nickname for using the logarithmic base of 10. It's the common logarithmic base. It's the logarithmic base that appears in your calculator when you press log, understood to be base 10. Then there's another very common logarithmic base, and it's base e. I'll tell you about where it comes from in a little while, but it's also used so often that it's given a nickname. That is, log base e of x is designated as ln x. So this is understood to be a logarithm in base e. So that's what that part is all about. Now, where does this e idea come from? E is a naturally occurring constant, kind of like pi is a naturally occurring constant. But pi, it's easy to understand where pi comes from. Pi is just the ratio of circumference to diameter within all the circles in the universe. Okay, fine. Where does e come from? How does it evolve? Where is its origin? Well, one explanation for the origin of e is this, that when you studied exponential functions, you found this to be the case. If you were graphing, let's say, 2 to the x power, then let's say it looks kind of like this. Okay, so this is 2 to the x power. And there is a certain slope of the tangent line at this point. And it turns out that the slope of the tangent line at this point, this slope, is slightly less than 1. Now, if you construct the graph of 3 to the x power, then its graph looks kind of like this. And its slope of the tangent line at this point is a value which is slightly greater than 1. There must be then a logarithmic, or excuse me, a base for this kind of function such that the slope of the tangent line at that point, at the point 0, 1, is exactly 1. And that is what E is all about. E is the base of an exponential function such that the slope of the tangent line at the point 0, 1 is exactly 1. So it occurs right about in this neighborhood, the graph does, and the value E then is near to 3. You see, this is the graph of E to the x power. And actually E is 2.7 and so on. It's an irrational value, never ending, never repeating decimal, kind of like pi. Okay, so that's the notion of where E comes from. Now, you talked about when you got into this logarithmic idea, it was probably very confusing at first, and you didn't know why you would need this, and then the need for the logarithmic idea became abundant after you learned about the properties of logarithms. Now let's talk about those properties. These are the properties as you talked about them in algebra. Here's what sometimes was called the product property or the product rule. The logarithm of a product, 5x means 5 times x. The logarithm of a product is the logarithm of one factor plus the logarithm of the other factor. Now notice I'm using natural log here because we're going to be using natural log a little bit later. But I could just as well be using log, I could be using any kind of base that I wanted to as long as it was common throughout the problem. But it's the idea that the logarithm of a product is the logarithm of one factor plus the logarithm of the other factor. That's the product idea. The quotient idea works in a similar way. The logarithm of a quotient means the logarithm of the numerator minus the logarithm of the denominator. And then there's a power property. The logarithm of x squared, x to some exponent, you see, you can take the exponent and make it the coefficient of the logarithm. You just move it to a position right here. This is 2 ln x. Now all of these properties have a lot to do with the properties of exponents. When you have a common base and you're multiplying like bases, you add exponents. When you have a common base and you're multiplying like bases, you add exponents. And that's just what we're doing here. We're adding exponents, basically, here. Now, there is a way to prove this algebraically. You may have seen it in your algebra class, and that's fine. We won't go into all of that, but these are the properties that I just want you to recall. There were certain very kind of special situations that are interesting and necessary for us to remember. ln e, remember this is the logarithm in base e. When the base and this number are the same in the logarithmic world, it turns out that this is 1. It's easy to see if you transfer this or change it from the logarithmic form to the exponential form, you see why this is the case. At any rate, and ln 1 turns out to be 0, and again you can see it very easily if you change it into exponential form. Now, all of these properties have kind of a two-way, they're kind of a two-way street. That is, the logarithm of a product is equal to the sum of the factors, logarithm of the factors. And you can go the other way with this. If you have this, you can write this. If you have this, you can write this. And that's true for all of these properties. Now, once you get accustomed to the properties, or you get exposure to the properties, then you began to work with the properties. You began to take expressions and use the property in one direction or another. And this was just in preparation for solving certain problems. Now, we're going to work with these properties in just a moment, but this power property right here is very useful in solving a problem like this one that we started with. Now remember that we were trying to solve this 2 to the x equals 5, and in the classroom you probably solved problems just like this. You said, okay, let's go into the logarithmic world. After all, we jump into the world of exponents by getting into the world of logarithms. So we apply the notion of logarithm on both sides. And we can use common logs or natural logs, but if we use natural logs, it looks like this. And by the power property, this becomes x ln2. Now, remember, ln2 and ln5, those are just numbers in the calculator. So this is just the coefficient of x. So we divide on both sides by that coefficient, and it turns out that x then is ln5 over ln2. And if you punch your calculator a little bit and resolve this, you'll find out the number associated with this, which is the number that corresponds to the exponent on 2 for us to give 5. Okay, and I'll let you go ahead and do this if you'd like. Well, at any rate, it gives us some latitude. These properties give us great latitude in solving certain kinds of problems. But let's go through the properties a little bit and talk about them. Now, here's where the history part of this discussion comes into play in what we're going to do in the calculus arena. The properties of logarithms are very, very useful. And incidentally, these properties are proven in your textbook in terms of the definition that we're going to talk about. They can be proven algebraically from our historical experience, but they also can be proven in terms of what we talk about too. Okay, let's see, ln 2x over y. Now let's suppose we want to expand this and write an expression in sort of an expanded form. We recall that the logarithm of a quotient is the logarithm of the numerator minus the logarithm of the denominator. So we would write ln 2x minus ln y. And then the logarithm of a product is the logarithm of one factor plus the logarithm of another factor, regardless of, and there could be several factors, as you can well imagine. Okay, so we've expanded the situation. Here's another one, same idea. We have 3 times e squared. So we have ln then of 3 plus ln e squared. And by the power rule, this becomes 2 ln e. And we recall that ln e is simply 1. So this is natural log of 3 plus 2. So we have expanded, we've simplified a little bit. Now the situation can be dealt with or practiced in reverse. That is, we can take sort of an expanded expression like this, and we can try to write this as the logarithm of a single item. And we can do that like this. When you're faced with an expression such as this, take the coefficients first and use that power rule. And we're sort of using it in the reverse of how we wrote it up here. We're thinking then that a coefficient out here becomes the exponent on this value. So this would become ln x cubed. And then this would become ln y squared. And this would become ln z to the 4th. Now, those factors that have plus signs, if we're adding logarithms, you see, then it's the logarithm of their product. When we're subtracting, we have a quotient involved. So we have both product and quotient idea involved in the same problem. I'm going to take my time with this. This sum of logarithms means the logarithm of x cubed y squared. And then I'll bring down this. You can do all of this in one step if you want to, down to this step, that is from here to here, if you want to, if you can see through this well enough. But just for practice, I'm putting in the extra step. I'm just taking care of this part first. And then this difference idea leads us to the logarithm of a quotient. So it's the log then of x cubed y squared over z to the 4th. Here's our definition of the natural log function. It is ln x is the definite integral 1 to x of 1 over t with x being positive. Now let's get a grip on what this means. It kind of looks mysterious right now, I'm sure. We're using a t here, we've got an x here. What is all of this about? The x is over here. How does all of this correspond? Well, it turns out that the number associated with ln of some particular x is, it corresponds with the area under the curve of the graph of 1 over t. Let me show you what I mean. I mean, if we're thinking about the graph of 1 over t, we're talking about a graph that has this kind of behavior. All right, now let's say that 1 is right here. Here's 1, here's 2, here's 3, and so on. Now, if we're talking about the integral, the definite integral 1 to x is positive now, so x falls into this, this interval from 0 to infinity. If we choose an x, for example, let's say right here, then we're talking about a number corresponding to the area of this region. And if we choose an x out here, then it's just the area of another region. If we're talking about an x that appears between 0 and 1, then we're talking about a region over here. You see, it's between that x and 1, wherever that may occur. Now, this is a, wow, this is a very interesting kind of way of defining logarithm. But it's rather convenient, too. I mean, think about the general integral, the integral function associated with 1 over t. If f of t is 1 over t, then f of t is t to the negative 1, and the integral function is t to the negative 1 plus 1 over 0, and this causes this situation to be undefined. So we have no definition for the general integral of 1 over t, and this gives us a little grip on that, that idea. Now, it may occur to you, you may think, oh boy, we're gonna be working with integration here a great deal. But it turns out the great power of this procedure comes in finding derivative. Take a look at this. If we have this, here's our basic definition now with x is positive. Take the derivative on both sides. Think about the derivative of this and the derivative of that. Now, consider the derivative of this. Now, does this look vaguely familiar? Remember the second fundamental theorem of calculus? This becomes 1 over x. So, it means that the derivative of ln x is 1 over x. Now, there's some power. If f of x is ln x, then f prime of x is 1 over x. Why is this man so excited, you say? Well, I'll tell you why. This has tremendous power when you involve the chain rule with it. If f of x is ln of some expression, now I'm just going to refresh your memory about generally how the chain rule works in the arena of natural log. If we let u stand for this expression, then f of u would be ln of u. And when we take the derivative of f, remember it was the derivative of f in terms of the single entity, and then the derivative of the single entity. Well, in terms of the natural log idea, f prime of u, if f of u is ln u, then f prime of u is 1 over u, from what we just discovered right here. And then times, we're going to take this expression and take its derivative. So it's just the derivative of the expression over the expression itself. It makes things really, really easy and powerful. And that's a worthy goal in mathematics, isn't it? You're looking for power and simplicity combined. Well, anyway, all right, if f of x is ln of x squared plus 1, when we're talking about the derivative of f of x being u prime over u, where u is just this expression, then it's really easy. U prime is 2x, and the expression is x squared plus 1. And that's as simple as it can get. Now, we can take this idea of using the chain rule, this u prime over u idea, and it may occur within a more complicated problem, like this. We could have g of x is x cubed times ln of this expression. Now, by the product rule, if we want the derivative of this, and we do, then it's x cubed times the derivative of this part, and then it is ln x cubed minus 5 times the derivative of the x cubed. So here's the layout of what we're going to do. Now, x cubed, and then the derivative of this is where the u prime over u comes in. The u prime here, well, let's see. The derivative of x cubed minus 5 is 3x squared. And then over u, that just means over that expression. And over here, it's the logarithm times the derivative of x cubed, which is 3x squared. So it's 3x squared times logarithm. And now it's a matter of cleaning up with a little bit of just a little manipulation. X cubed times this numerator, we get 3x to the 5th over the expression, and then plus this other thing that we just brought down. So a very simple idea, very powerful idea. Here's an example involving a radical. F of x is ln of the square root of x plus 1, and we want to take the derivative. Now, let's massage this a little bit, thinking of the radical as a fractional exponent, and now using that power rule of logarithms, so the 1/2 becomes the coefficient. And now we're ready to go with our derivative. F prime of x then would be, by using the product rule, 1/2 times the derivative of this, and then plus the logarithm of the expression times the derivative of 1/2. The derivative of 1/2 is 0, so this term disappears very quickly. All right, back over here, we have the derivative of the logarithm part is the u prime over u. U prime of x plus 1 is 1, and u is the expression itself, x plus 1. So the derivative of f turns out to be 1 over 2 times x plus 1. Again, a very simple outcome for this situation. Well, the idea of using this logarithm, it's so simple that maybe we can make use of it in situations that don't even involve a logarithm. And that turns out to be the case. That here, for example, if we have this, this function and we want its derivative, what we can do, we can use a technique that puts us into the logarithmic world and allows us to use some of the power that we have just discovered. And it works like this. Take the log, the natural log on both sides, and we have this. All right, now let's massage this a little bit. Let's clean this up algebraically, and then we're going to take the derivative on both sides. All right, so here this becomes the fraction to the 1/3 power, or 1/3 ln fraction. All right, but the ln fraction means the log of the numerator minus the log of the denominator. So we have 1/3 times log of numerator minus log of the denominator. All right, good. Then the 1/3 times each of those terms becomes this. Now we want to take the derivative on both sides. The derivative of ln y is y prime over y. And now over here, the derivative, now I've left this blank. This is where we're going to kind of pick up the problem. We want the derivative of all of this, and it means by the product rule for these terms, it's 1/3 times the derivative of this. So it's 1/3 times the derivative of this, the u prime over u. That would be 2x over x squared plus 1. And then plus this times the derivative of that, and it goes out. Okay, so that term's gone. All right, back over here. Then we have minus 1/3 times derivative of this. That's the u prime over u business. So we have 2x over the expression x squared minus 1. And then the other term involved here is the natural log times the derivative of 1/3, which is 0. So that goes out. So we have this. Now it's a matter of cleaning this up. Now, notice the 1/3 appears in both of these terms. And I have factored the 1/3 out, and we're going to move our problem up here, leaving the y prime over y on the left side. All right, here we go. Y prime over y on the left side. I have factored out the 1/3 from the two terms. And here's what we have. Now, we have a couple of fractions. We'd like to bring them together. We need a common denominator. It turns out that the common denominator is the product of these two. And incidentally, in using the laws of logarithms a few moments ago, let's backtrack a little bit. I forgot to mention this when we came to it. But right in here, we could have factored the x squared minus 1. It doesn't save us anything, in my view, to do this, but we could have written this as x plus 1 times x minus 1, and then we could have expanded this situation even further. but it's just a manipulation that could have occurred right here. It turns out there are several ways of attacking these problems. But anyway, let's go on back over here. The common denominator is actually the product of these two, so it's x to the fourth minus 1. So in order for us to collect the two fractions, we'll have to multiply this fraction by x squared minus 1 over x squared minus 1, and that's what I've done here. And to rewrite this one in the common denominator form, I'll multiply both numerator and denominator by x squared plus 1. So it's 2x times x squared plus 1 over x to the fourth minus 1. All right, now that we have common denominators, we can bring these two together. So we have 1/3 here. The 2x times x squared is 2x cubed. The 2x times minus 1 minus 2x. Here, minus 2x times x squared is minus 2x cubed. The 2x times 1 is 2x, so it's minus 2x. All right, then collecting like terms, 2x cubed minus 2x cubed, they go out. And we have minus 2x, that's minus 4x over x to the fourth minus 1. Now, we still have not resolved the situation, you know. We still have y prime over y. And what we're trying to do is take the derivative of the y up there, so we want to write y prime. So we're still not done. So let's go up over there. This is really negative 4x over 3 times x to the fourth minus 1. That's what I have written over here. Now recall that y, from the very beginning, the very first statement for the problem was y equals cube root of some kind of fraction. And so when I multiply on both sides by y, I am writing over here, I'm writing the y, which is this. It's the cube root of that big fraction. Now, some teachers might say, well, it's okay to leave it in this form and we're pretty much finished, but we can manipulate it a little more algebraically if we want to. After all, these factors in here are contained within x to the fourth minus 1. In other words, we can write this as 4x in this numerator, and factoring here we get x squared plus 1 times x squared minus 1, and this is just numerator to the 1/3, denominator to the 1/3 power. And now we can, well, let's see, we've got x squared plus 1, x squared plus 1 to the 1/3. So we have x squared plus 1 to the 1 minus 1/3, or x squared plus 1 to the 2/3 power, still in the denominator, and then multiplying these two like terms, x squared minus 1 to the 1 plus 1/3, or 4/3, again in the denominator, leaving the 4x in the numerator, the minus sign, and the 3 as a factor in the denominator. So anyway, this is a lot of algebraic manipulation, but in some situations, it helps us time-wise to go through the gymnastics of moving into this logarithmic world in order to accomplish this derivative idea. I can't help but relay a story to you about a former student. I ran into a student one time in a hallway, and I had had this student for college algebra and trigonometry, and I knew that he had gone on to calculus. Stopped him in the hallway. I said, Eric, how you doing? He said, fine. I said, how are you doing with calculus? He said, you know, he says, calculus is really easy to understand. But, he said, I'm having trouble with the algebra within the calculus. And he said, what you told me about showing all the steps and so forth was really important, and I didn't realize that it was really important. He and I had had a thing going on for a long time. I had had him as a student for several semesters, and we talked extensively about showing all your work and all of the steps and so forth. This is where it really comes into play.